Are genes your fate? Which is more important, nature or nurture? So, what are they? Nature represents genetic makeup. These are the genes that are inherited, whilst nurture represents environmental factors, which include experiences, life choices, and upbringing. Both nature and nurture can influence chronic disease. The Australian Institute of Health and Welfare defines chronic illnesses as illnesses that are prolonged in duration, do not often resolve spontaneously, and are rarely cured completely. They continue on to explain that while some chronic diseases make large contributions to premature death, others contribute more to disability. According to the World Health Organization, the four most common chronic diseases includes cardiovascular disease, chronic respiratory disease, diabetes, and cancer. The importance and role of nature versus nurture will be investigated in the top two most prevalent chronic diseases, being cardiovascular disease and chronic respiratory disease. Cardiovascular disease is an umbrella term for all diseases and conditions involving the heart and blood vessels. Hypertension is a prevalent cardiovascular disease. The heritability of hypertension is widely recognized, with up to 30 to 50% of hypertensive cases being attributed to genetic heritability. Dixon and Sigmund report correlation between plasma angiotensinogen, or AGT, and high blood pressure, with studies showing decreased blood pressure with administration of anti-AGT antibodies, increased blood pressure with injection of AGT, and elevated blood pressure in animals with AGT transgenes. The other 50% of cases of hypertension are attributed to environmental factors. Kim and Lee identify lack of physical activity, excessive alcohol consumption, and high sodium intake as major causal factors of hypertension. Interestingly, Butler stated that there is no known single gene playing a major role in hypertension, but rather many genes, each with mild effects reacting to different environmental stimuli. Balasina, Lenzani, Maninatu, and Bianchi explain that there are environmental factors, salt for instance, that produce the hypertensive effect only in the presence of a particular genotype and vice versa. Chronic respiratory diseases involve the airways and the lungs, with the most common disease being chronic obstructive pulmonary disease, also known as COPD. Hardin and Silverman investigated the attribution of genetics in developing COPD, with recent genome-wide association studies identifying several genomic regions that are clearly related to COPD susceptibility. There is evidence that severe alpha-1 antitrypsin, or AAT, deficiency is heritable and contributes to COPD. Hardin and Silverman further suggest that up to 60% of individual susceptibility to COPD could be explained by genetic factors. The remaining 40% are influenced by environmental factors such as tobacco smoke, childhood respiratory infections, air pollution, and occupational exposure. In fact, about 15% of COPD cases are due to occupational exposures to pollutants at the workplace. Interestingly, only 10 to 20% of all heavy smokers develop COPD, and approximately 25% of those diagnosed with COPD have never smoked. Walter, Gottlieb, and O'Connor state that it is likely that multiple genetic factors interacting with each other and with a number of environmental agents will be found to result in the development of COPD. It appears that nurture shapes nature, with scientists now investigating the role of epigenetics. Epigenetics refers to the heritable changes in gene function due to environmental factors. Epigenetic mechanisms such as DNA methylation, nucleosomal histone modifications, and non-coding RNAs control gene expression through regulation of chromatic structure and function and post-transcriptional mechanisms without altering the underlying DNA sequence. During pregnancy, environmental factors such as undernutrition, overnutrition, exposure to toxins, and stress can all influence future disease. Zanchetti found that paternal environmental factors before conception and even during sperm development determine the health of a child. Not only do they influence the individual exposed to, for example, smoke inhalation, it also affects their offspring and the generation after that. Studies on identical twins show how, although genetically identical, environmental factors can over time alter their genes, making them different. But how does genetics contribute to chronic disease? Sharma, Kelly, and Jones explain that disruption of epigenetic processes can lead to altered gene function and malignant cellular transformation. During cancer formation, as seen in the diagram, a large number of epigenetic modifiers are mutated, amplified, and at the same time, epigenetic changes such as DNA methylation, histone modifications, and microRNAs lead to abnormal gene expression, which induce genome instability. In breast cancer, for example, changes include DNA hypermethylation, increased histone modifications and enzymes, and downregulated microRNAs. Again, in breast cancer, microRNAs such as MIR21 can be found to be amplified, which often increases the risk of developing mets to the lungs. The influence of nature and nurture cannot be divided, as it is clear that both play key roles in the development of chronic disease. It is, however, clear that nature cannot be controlled, whereas our environment and lifestyle choices can be controlled. Our environment and lifestyle choices interact with our genes, suggesting that nurture has a greater influence than nature in the development of chronic disease. An article by Slattekin compared the roles of nature and nurture in the development of chronic disease. It was found that while genetics pose a large risk in disease heritability, epigenetic factors play a larger role in the disease risk, which can also be passed down through generations.